the WOW signal. On August 15th, 1977, the Big Ear radio telescope at Ohio State University recorded a burst of radio energy from the direction of the Sagittarius constellation that lasted 72 seconds, arrived at 1,420 megahertz, the precise frequency of neutral hydrogen, and was 30 times more powerful than the background noise surrounding it. Astronomer Jerry Eman, reviewing the printed data several days later, circled the sequence in red ink and wrote one word in the margin, "Wow." The signal has never been detected again. In the nearly 5 decades since no telescope, no follow-up observation, and no independent confirmation has produced anything that resembles it. What makes the WOW signal disturbing is not just that it arrived at the exact frequency CD researchers had long identified as the most likely channel for intentional interstellar communication, the frequency of the most abundant element in the universe. It is that it arrived exactly once, with perfect characteristics for a signal of intelligent origin, and then stopped as if whatever produced it either ceased, moved on, or never intended to repeat itself. The most recent serious attempt at explanation, published in 2024 by a team at the Planetary Habitability Laboratory in Puerto Rico, proposes that the signal was produced when a magnetar, a type of hypermagnetized neutron star, flared, and the radiation struck a cold cloud of neutral hydrogen, exciting it briefly into radio emission at the hydrogen line frequency. The math, the team argues, works. The phenomenon would be rare, brief, and non-repeating, which fits everything known about the WOW signal. Not everyone agrees. Other astronomers note that the initial source of radiation powerful enough to produce such a flare has never been identified in the direction of Sagittarius, and that the proposed mechanism has never been directly observed in any other context. As of 2026, the signal remains officially unexplained. The International Astronomical Union has no category for it. It sits in the literature as a data point with no confirmed origin, no mechanism, and no repeat, which is either the most ordinary kind of unexplained anomaly in radio astronomy or the one time in human history that something deliberately aimed a transmission at us. We detected it for 72 seconds, and then we missed every repetition that followed. The Big Ear telescope itself was demolished in 1997 to make way for a golf course expansion. The instrument that caught the only signal of its kind was destroyed before the signal was ever explained. The Pioneer Anomaly. In 1972 and 1973, NASA launched Pioneer 10 and Pioneer 11, the first spacecraft designed to travel through the asteroid belt and the outer solar system, eventually heading toward interstellar space entirely. For decades after their launches, scientists tracking both probes noticed something that should not have been happening each year. Both spacecraft were falling behind their predicted positions by approximately 5,000 kilometers. Something was decelerating them very slightly beyond everything that gravitational models could account for. For over 30 years, the Pioneer Anomaly, as it became known, was one of the most actively discussed, unsolved problems in physics. Proposals to explain it range from mundane, a gas leak, a software error, an unmodeled gravitational body, to genuinely revolutionary, a flaw in our understanding of gravity itself, a modification of Newton's laws at large distances from the sun, perhaps even evidence that dark matter behaved differently than current models suggested. For a period in the early 2000s, it was seriously discussed in peer-reviewed physics literature as a potential indicator that the standard model of physics needed revision. Then, in 2012, a team led by Slava Turishev at NASA's Jet Propulsion Laboratory published a resolution that satisfied most of the scientific community. The deceleration was caused by the uneven emission of heat from the spacecraft's own power systems. The radioisotope thermoelectric generators aboard each Pioneer ran warm, and the heat they radiated was not symmetrical. More warmth escaped in the direction of travel than away from it, and photon pressure from that asymmetric heat output, tiny but consistent and cumulative, over billions of kilometers, pushed gently against the spacecraft's forward motion. The effect was small enough that it had taken decades of recovered archival data and a reanalysis of more than 75,000 pages of original records to demonstrate conclusively. The resolution satisfied most physicists. What it leaves is something equally unsettling for 30 years, a real anomaly in real data, went unexplained, was seriously entertained as evidence of new physics, and turned out to be heat. The question the Pioneer Anomaly raised, whether something unknown is acting on distant spacecraft, was eventually answered. But the reason the question lasted 30 years is that the data was genuinely ambiguous for 3 decades, and everyone looking at it was working within the limits of what had already been recovered and analyzed. The full data set needed to close the case had been sitting on magnetic tapes in boxes under a staircase at JPL since the 1980s. The resolution required volunteers to run more than 75,000 pages of original data through optical character recognition software, supervised by human validators who checked each page. The answer to a 30-year mystery in physics was in a box that nobody had opened. Oumuamua. On October 19, 2017, astronomer Robert Warwick, working with the Pan-STARRS 1 telescope at the University of Hawaii, detected an object moving through the solar system on a trajectory that made it unlike anything ever previously recorded. Its path was hyperbolic. It had come from outside the solar system, entirely passed closest to the Sun on September 9th, and was now departing. It was the first confirmed interstellar object ever detected passing through our solar system. Astronomers named it Oumuamua Hawaiian for a messenger from afar arriving first, and had approximately 2 weeks of useful observation time before it faded beyond detectability. Those 2 weeks produced a list of properties that, in combination, don't match any class of object previously cataloged. Oumuamua was extremely elongated, with an aspect ratio estimated at somewhere between 5 to 1 and 10 to 1 more elongated than any asteroid or comet previously observed. It had no visible coma, no dust tail, and no detectable gas emissions of any kind, despite moving close enough to the Sun to be significantly warmed. It was accelerating beyond what gravitational forces alone could explain, moving away from the Sun faster than pure solar gravity would permit. That acceleration in a known comet would be explained by outgassing the jetting of material from the surface as ice warms and evaporates, creating thrust. But Oumuamua showed no visible outgassing. The combination of these properties led Harvard astrophysicist Avi Loeb and his co-author to publish a paper in 2018 formally exploring the possibility that Oumuamua was a piece of alien technology, specifically a light sail, a thin low-mass reflective surface pushed by solar radiation pressure, which would account for the anomalous acceleration without requiring any visible outgassing. Most astronomers regarded this as a last resort hypothesis. In 2023, astrochemist Jennifer Bergner and astronomer Daryl Seligman published an alternative in the journal Nature. Oumuamua was a comet from another solar system that had accumulated trapped molecular hydrogen inside water-rich ice during its interstellar journey, and that hydrogen was released as solar warming reached the object's interior, providing an invisible, undetectable thrust. The model, they argued, accounts for both the acceleration and the absence of a visible coma. As of 2026, the hydrogen hypothesis represents the scientific consensus, and most researchers consider the question closed. A minority, including Loeb, maintain that the hydrogen model has not been definitively proven, and that no definitive natural explanation for the object's full set of anomalous properties has been established to scientific certainty. Oumuamua is now too distant to observe by any existing telescope. Whatever it was has already left the solar system. The window to know for certain closed in November 2017. In 2019, a second interstellar object designated 2I/Borisov passed through the solar system and behaved exactly as a standard comet should, complete with a visible coma and tail. Its normality, in contrast to Oumuamua's catalog of anomalies, made Oumuamua's properties harder to dismiss, not easier. The Fermi Paradox. There is no date attached to this mystery because it has been accumulating evidence for the entire history of modern astronomy. The observable universe contains an estimated 2 trillion galaxies. Our own galaxy alone contains somewhere between 100 and 400 billion stars. A substantial fraction of those stars are now known to host planetary systems. The fraction of those planets that fall within the habitable zone of their star where liquid water could exist at the surface is not known precisely, but conservative estimates place it in the billions for our galaxy alone. The universe is approximately 13.8 billion years old. which means that for most of its history, other civilizations would have had the opportunity to develop technology far more advanced than ours. If even a small fraction of those billions of potentially habitable worlds had produced intelligent life, and if even a small fraction of those civilizations had developed interstellar travel or communication, the galaxy should statistically be full of detectable evidence of their existence. It is not. This is the Fermi Paradox, first articulated by physicist Enrico Fermi in 1950, when during a lunchtime conversation about flying saucer reports, he asked the question that has never been answered: where is everybody? Every serious attempt to resolve the Fermi Paradox produces an answer that is disturbing in a different direction. Perhaps complex life is extraordinarily rare, and we are statistically alone in a universe large enough to make that statistically plausible, but no less lonely. Perhaps intelligent civilizations reliably destroy themselves before reaching the technological capability for interstellar communication, and the silence we hear is the silence of civilizations that have already collapsed. Perhaps the conditions for intelligent life are far more specific than current models suggest, and the vast majority of habitable planets produce only microbial life for billions of years. Perhaps civilizations advanced enough to be detectable are actively choosing not to be detectable for reasons that by definition we are not yet in a position to understand. Perhaps signals exist that we have already detected and simply classified as noise. Perhaps we are surrounded by signals and have simply not yet recognized their form. Each of these answers requires accepting something deeply uncomfortable about either the nature of the universe, the nature of intelligence, or the nature of our own future. The Fermi Paradox is not a mystery that will be solved by a single discovery. It is a silence that has to be accounted for, and every accounting leads somewhere unsettling. Fast radio bursts. In 2007, astronomer Duncan Lorimer, sorting through archival data from the Parkes Radio Telescope in Australia, found a record of a millisecond burst of radio energy so intense and so brief that nothing in the standard model of known astrophysical phenomena could easily explain it. The event had actually occurred in 2001 and been sitting unnoticed in the data for 6 years. It was labeled the Lorimer burst and became the first documented fast radio burst, or FRB, a class of radio transient whose energy output in milliseconds can equal the total energy the sun emits over several days. They appear to originate from billions of light years away outside our own galaxy. Some of them repeat sending bursts at irregular intervals from the same source. Some appear only once and are never detected again. As of 2026, hundreds of FRBs have been cataloged. The mechanism that produces them is still not conclusively established. The leading scientific consensus attributes them to magnetars, highly magnetized neutron stars whose powerful magnetic fields periodically snap and release enormous bursts of electromagnetic energy. In 2020, a fast radio burst was detected from within our own galaxy, for the first time originating from a known magnetar designated SGR 1935 plus 2154. This was significant because it confirmed that at least some FRBs can be produced by magnetars, but it did not conclusively establish that all fast radio bursts come from magnetars, and the repeating ones in particular present challenges that the current magnetar model does not fully resolve: why some sources repeat regularly and others never repeat at all, why some bursts come in clusters and others in isolation, and why the energy output varies so dramatically between events at apparently similar source distances. What makes fast radio bursts disturbing beyond their unexplained mechanism is their scale. An event that lasts a few milliseconds and releases more energy than the sun produces in days from a source a billion light years away, that we can observe at all only because radio waves happen to travel easily through intergalactic space, is not something human intuition is equipped to process naturally. The universe, it turns out, produces events of that magnitude routinely in categories we only discovered because an astronomer was looking through old data and noticed something that had been sitting there for 6 years. The Hubble Tension. Sometime around 1929, Edwin Hubble confirmed that the universe is expanding, establishing the proportional relationship between a galaxy's distance from Earth and the speed at which it appears to be moving away. The constant that describes this proportional relationship, now called the Hubble constant, has been refined continuously ever since. The problem is that two completely different and completely independent methods of measuring the Hubble constant produce two different answers that cannot both be right, and neither method appears to have the kind of error that would reconcile them. The first method measures the rate of expansion in the early universe using the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang, itself mapped in extraordinary detail by the Planck satellite. This method gives a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec. The second method measures the rate of expansion in the local present-day universe using distance ladders built from Cepheid variable stars and Type 1a supernovae objects whose intrinsic brightness is known and can therefore be used to measure distance. This method gives a Hubble constant of approximately 72 to 74 kilometers per second per megaparsec. The gap between these two numbers, known as the Hubble tension, is small in absolute terms, but enormous in significance. It falls well outside the margin of error of either measurement, and it has remained stubbornly persistent, as both measurement methods have been refined, tested, and retested by multiple independent teams using different instruments. The tension has two possible categories of explanation, and neither is comfortable. Either one or both measurement methods have a systematic error that no one has yet identified despite decades of checking, or the standard model of cosmology is wrong in some fundamental way. And the universe is either expanding at a rate that changes in ways current models don't predict, or contains some component, perhaps some form of dark energy, that behaves differently at different cosmic epochs that current physics does not account for. As of 2026, the Hubble tension remains unresolved. It has been nominated by multiple physicists as the most important problem in cosmology, the measurement that is most likely to crack open a new understanding of how the universe actually works if and when it is ever explained. And if you enjoyed this video, subscribe for similar ones, and feel free to drop suggestions for the next video in the comments below.